Hi, this is Mr. Asher, and this is for Chem 121. And I'm going to go through a couple of things about uh, looking at combustion products and figuring out what the oxidation state of different atoms are. And then we'll work through that, and I'll show you how you figure that out and look at that. So the reaction that we're going to look at, share my screen, is this one. It is the combustion of butane. So we have two butane molecules, C4H10 plus 13 oxygen molecules going to 8 CO2 plus 10 H2O. And the question is how you figure out the oxidation states of everything in here and how you figure out what's oxidized and what's reduced. And this is sort of a model for how you go about this. And combustion problems are a little odd because, and let me go over here and now let me turn on my whiteboard. Share. Oops, that's not what I wanted to do. Share whiteboard there. Better. And combustion products are weird because they're redox processes. So we have 2 C4H10 plus 13 O2 gives us 8 CO2 plus 10 H2O. And we know it's a redox process because we're starting off here with elemental oxygen. So oxygen here has an oxidation state of 0 because anything bonded only with itself has a state of 0, right? The rationale there is that the electrons are shared equally, so neither oxygen atom is taking electrons from the other, so its oxidation state is 0. But then when oxygen is bonded to anything else, with the exception of perhaps fluorine, when it's bonded to anything else, oxygen has an oxidation state of 2 minus, okay? Always, right? So that means the oxygen in CO2 is 2 minus, and the oxygen here is 2 minus, right? And now the other thing that you always know is that hydrogen is always plus 1. One plus, right? So hydrogen is always 1 plus. And that makes sense because if you aren't quite clear, because if hydrogen is plus 1, right, we have 2 times plus 1, 2 times 1 plus is equal to 2 total plus charges, which balances out the 2 negative charges we get from oxygen, so that a water molecule is electrically neutral, right? You get 2 times plus 1 from here, and you get 2 minus here, and everything is neutral, right? And over here you get 2 times 2 minus for 4 minus on oxygen, which means that carbon has to be 4 plus, okay? Right? Everybody hopefully follows that. If you have 2 oxygen atoms, each one is 2 minus, the total negative charge there is 4 minus, right? Which means to have CO2 be electrically neutral, which it has to be, carbon has to have a formal oxidation state of 4 plus, okay? So hydrogen started out as 1 plus, and it ends as 1 plus. If we look at this, hydrogen starts out as plus 1, and it ends as plus 1. So hydrogen doesn't take part in the redox process at all. It's just along for the ride. Oxygen starts out as 0, and it ends as 2 minus, which means that oxygen plus 2 electrons gave me oxygen 2 minus. So oxygen was reduced. Right? So the only other thing left that could be oxidized is carbon, right? And now to understand why carbon gets oxidized, let's take a look at what a butane molecule looks like. So we have a carbon, we have 4 carbons all linked together. And then each carbon has to be bonded to 4 things. So all of the remaining spaces around a carbon are taken up by hydrogen. Right? Right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 hydrogens. Each hydrogen has a charge of plus 1, right? The carbon-to-carbon bond doesn't count, but the total positive charge around this carbon is 1, 2, 3. So the total positive charge is 3 plus, which means this carbon has to be 3 negative. Right? Around this carbon, there's a total charge of 2 plus, which means that this carbon is 2 negative. Same for this carbon. This carbon is 2 negative, and this carbon is 3 negative. Yeah, right? So carbon does two things. One, in one instance, it starts out as 2 minus, and then it gains 6 electrons to become, I'm sorry, it starts off as 2 negative. Sorry, oops. Carbon is being oxidized. And it ends up as carbon 4 plus 6 electrons. And how did I get 6? Well, it goes down from -2, or it goes up from -2 to +4. And so if we just think about that in terms of jumps, it's starting down here at -2, and it jumps up -1, 0, 1, 2, 3, 4. 1, 2, 3, 4. And each one of these steps, from here to here, you get an electron. Here to here, get an electron. Here to here, get an electron. Electron, 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 until you get a total of 6 E minus, 6 electrons. Okay? Hopefully that's clear. All right? So that's these two carbons. This carbon and this carbon each give up 6 electrons. And then we have this carbon, the carbons on the end, C3 minus goes to C4 plus 7 electrons. All right? So we have 2 carbons that do this, and we have 2 carbons that do this. So the total number of electrons we get off a carbon are 2 times 6 E minus, and then plus 2 times 7 E minus, right? So this is 12 plus 14 is 26 total, right? So 26 total electrons are given up by the carbons. And here we have 13 oxygens, 13 times 2, 13, 13 times 2 minus is equal to 26 electrons. And that is convenient. And if this doesn't balance, then we have a problem. But we have oxygen taking up 26 electrons, and we have carbon releasing 26 electrons. So everything balanced. So for this combustion reaction, you would say carbon is oxidized, except there's two different things. Carbon 2 minus goes to carbon 4 plus 6 electrons. And then carbon 3 minus goes to carbon 4 plus 7 electrons. And this is the oxidized, this is carbon being oxidized. And oxygen, why I haven't spelled that, is reduced. And oxygen goes to 2 electrons plus oxygen goes to oxygen 2 minus, right? And what you'll see is that in each one of these equations, we have charge balance between the left and the right side. There's 3 negative charges over here in total. Here there's 4 plus 7 negative, which is 3 negative total. And up here there's 2 negative total, and here there's 2 negative total on the right side. 2 negative total here, 2 negative total there, right? So that's how you do that. That's how you look at that balancing of oxidation and reduction, and how you figure that out and look at it. And now we'll look at, let me do another example that maybe is a little less confusing in terms of the oxidation states. So let's look at a really simple reaction. So we've got Mg solid plus, hold on just a second here, Mg solid plus nitric acid, HNO3, goes to magnesium nitrate plus H2. And we need to balance this equation. So let's see, we're going to need 2 nitric acids, and then I think that's balanced. 1 magnesium, 2 nitrates. Yeah, okay, so that's balanced. All right, so now, is this a redox reaction? Yes, clearly it's a redox reaction because you have magnesium in its elemental state here. So magnesium is starting out in oxidation state 0. And then over here, it's ending up bonded to 2 nitrate ions. Each nitrate ion is NO3 minus. How did I know that? I just know nitrate is NO3 minus. If you don't know that, you're probably going to have to go to the textbook and look up what the charge is on the nitrate ion, right? But because I know that, I don't have to do that, and so that's why I'm not doing that. But it's relatively trivial. It's relatively simple to figure out what the charge is, and so that means we've got 2 1 minus charges here from the nitrate for a total of 2 negative, and this whole thing has to be electrically neutral. So that means Mg has to be 2 plus, which means that Mg 0 went to Mg 2 plus 2 electrons. Okay, so magnesium got oxidized. How did I get there? It's just logic. It isn't walking a higher plane of consciousness. It's recognizing that magnesium in its elemental state as a solid has an oxidation state of 0. And over here, it has to be charged because this thing has to be electrically neutral. Magnesium nitrate has to be electrically neutral. So that means magnesium went from 0 to 2 plus. The only way it can do this is by losing 2 electrons. In other words, magnesium was oxidized. Oxidized. There we go. Okay. Now, conversely here, because we know NO3 is 1 minus, we know hydrogen here has to be H1 plus. Why? Because this has to be electrically neutral too. If nitrate is 1 minus, then hydrogen has to be plus 1. But over here, hydrogen is its elemental state, right? Hydrogen bonded to hydrogen, so hydrogen went to 0. Went to 0. Which means that hydrogen in the plus 1 had to gain 1 electron to go to hydrogen 0, right? So hydrogen was reduced because it gained electrons, okay? And if we look at this, we have 2 hydrogens did this. So that means 2 electrons were chewed up by hydrogen, were taken up by hydrogen, and each magnesium released 2 electrons, which works for the stoichiometry of the equation, okay? Working with oxidation reduction reactions is an exercise in logic. It isn't an exercise in understanding deeper facts, I guess, if you will. What you're trying to find is things that have changed charge. And to do that, you have to know certain things about common items you'll find. And the common things that you will know, or you should know, is that oxygen, when it's bonded to other things, is 2 minus. Hydrogen is plus 1. I suppose I should write that the other way down, is 1 plus, right? And then you should learn that that SO4, the sulfate ion, is 2 minus. Phosphate, PO4, is 3 minus. Nitrate, NO3, is 1 minus. Ammonia, NH4, is plus 1, right? Sometimes you'll recognize that iron can either be 2 positive or iron can be 3 positive. 3, a charge of plus 2 or plus 3, and the only way you can figure it out is by seeing what it's reacting with. If it's FeNO3, 2, meaning I've got 2 meaning I have two of these NO3 groups, each with a negative charge. That means that this iron is in the 2+ state, right? However, if it's Fe2SO4 3, I know that each SO4 carries a 2- charge, and I have 3 of them for a total negative charge is 6-, and that has to be balanced by 2 irons, right? So that means each iron is 3+, because 2 times 3+ gives me 6+ to balance the 6- I got from the sulfate. See, it's simple arithmetic and it's logic that I know compounds have to be electrically neutral, right? I know the total charge on this has to be 0. I know the total charge on this has to be 0. And if I remember that nitrate is -1 and that sulfate is -2, I can work out what the charge on iron has to be, right? And from that, I get its oxidation state. So if I see something like Fe plus H2SO4 going to Fe2SO4 3 plus H2, and I'm trying to balance that, right? I would recognize that, okay, iron went from 0 to iron 3+. Why do I know that? Because it started out as 0, it's elemental iron here, and over here it's bonded to 3 sulfate ions for a total of -6, so it has to be 3+, right? There's a lot of logic like that that's involved, but it's logic based on remembering what the charges are on ions. So you have to memorize this, or at least be able to look it up and say to yourself, okay, I think nitrate is -1. And then go into the book and look at, or use Google and search on what the charge on the nitrate ion or sulfate ion, right? Things like that. That's how you do it, and that's how you approach it. It's a sort of a logic puzzle. And if you do enough of them, you'll start to recognize the things that are being oxidized and reduced. And the trick is on an equation is to find, if you think it's a redox process, is to find things that started as elements and ended as compounds, or started as compounds and ended as elements, right? Or if oxygen is involved on one side or the other, right? If you have molecular oxygen on one side or the other, chances are it's a redox process, right? Anytime you're producing an elemental gas, but that just falls under the rubric of elements. Look for metals changing charge. Iron going from 2+ to 3+. Iron 3+ Fe, right? Things like that. Metals changing charge, right? So that's what you're trying to look for. And hopefully you find this interesting, and I'm going to stop there.